Welcome to the 4.4 instructional video. Just going to talk about some of those skills we need to do 4.4. And probably the big one that trips students up is factoring a quadratic that doesn't have a variable squared and a variable to the power of 1. It has an expression. And we saw this back in 20-1. I always like to start with one of those. So let's say we had t plus 1 squared plus 6 times t plus 1. And then plus, that would make it an easier one. So let's just say 5. Now, the part that students struggle with is that they try to expand it sometimes, but the big issue is that we have t plus 1 squared here, and then t plus 1 to the power of 1 there, and that does make it a quadratic expression. Depending on how comfortable you are with doing this, some of you maybe have done a substitution, so you could have said that x is equal to that t plus 1 bracket, and then we can rewrite that top expression as x squared plus 6x plus 5. And then it's our standard factoring. If you've had me before, you probably recognize this little t-chart where the numbers have to multiply to the constant, which is 5. They have to add to the coefficient of the degree 1 term, which is 6. And we can run through the factors. I chose 5 because it has, it's a prime number, so that makes it a little bit easier. And there are still two sets of those factors. There's only two factors, but the 1 and the 5 can be positive together or negative together. I think it's pretty, I hope it's pretty clear which one it's going to be. 1 times 5 is 5, and 1 plus 5 is 6. So in that factored form, we would have x plus 1 and x plus 5. All right, now the important condition here, or condition, the important concept is that the original question didn't have x in it. So that can't be our final answer. And we have to make sure we do this substitution again at the end. And so what we would have, and you need a couple sets of bracket for this, is in one bracket t plus 1 plus 1, and in the other bracket t plus 1 plus 5. Now, certainly most textbooks will clean up those brackets, and they would finish this with t plus 2 times t plus 6. I always like students showing me this step right here because it does pretty clearly indicate that you can factor that expression. All right, the reason why this is important today is because what we're going to be running into in 4.4 is trigonometric quadratics. So maybe cos squared x minus 3 cos x minus 10. Now, that is still a quadratic expression because we have cos being squared, cos to the power of 1, and then a constant at the back end. What I would highly recommend is rewriting this cos squared x term as in a bracket cos x squared minus 3 cos x minus 10. And that does tend to help students to picture why this is quadratic. You can make that substitution. I get a little lazy in trigonometry. I typically make that c is equal to cos x, which means we have c squared minus 3c minus 10. Hopefully you've done a ton of factoring up to this point. So I'm going to jump right to the factored form, which is c minus 5 times c plus 2. And then the final step is to make that substitution again. And I get cos x minus 5 times cos x plus 2. Now, the reason that we're talking about this is that if I made this an equation by making it equal to 0, and it has to be equal to 0, then when I get to the bottom line, I'll just put equals 0 at every step here. This bottom line has a big advantage because if I have, and I'll do it in two colors here, the red factor and the blue factor equal to 0, then one of those factors has to be 0. So what we get is two what I like to call solution trees. We have cos x minus 5 is 0, which is cos x is equal to 5. This has no solution, and we'll talk about that in a few minutes here. Cos x plus 2 could be equal to 0, which leaves me with cos x is negative 2. And again, probably a bad example. I'm more focused on the factoring itself, but neither of those two have solutions. And we have talked about this kind of briefly in chapter 4, but if you are taking the cos of an angle, it is always less than or equal to 1 and greater than or equal to negative 1. Now, one of the consequences of that is that if you are taking the inverse cos of an angle, that automatically introduces a domain restriction, and x has to exist from negative 1 to positive 1, or as an inequality, x would have to be less than or equal to 1 and greater than or equal to negative 1. Now, that is really important that as you're working through these problems, if you get that the cos, or sine for that matter, of an angle is greater than 1, that cannot happen. I really like, introducing the unit circle when we talking about the unit circle. And if you look at that unit circle with, the condition in mind that the unit circle gives me the value of the cos of an angle or the sine of an angle, the highest value of y is positive 1. the lowest value of y is -1, and we see that similar concept with the x values as well. And that really lets us know that the cos of any angle has to be in between, inclusively, -1 and +1. That's really important to remember in these concepts, and as we work through the examples, you really see that if I did get a statement like the cos of an angle is equal to 5, I can immediately say that there are no solutions to that. And again, a bad example because both of these yield no solution. Okay, make sure you do watch the examples and take those notes and chip away at the homework.